Hello everyone, welcome to the part 3 of the CFD interview questions for beginners and interns. Welcome to CFD first. We will be continue with the part 3 now. So the third part is basically revolves around the CFD software. So the first question is, what are the basic steps in a CFD simulation? So there are the 4 steps which are pre-processing, setup, solution and post-processing. Pre-processing is where we define the geometry, we generate the mesh and we assign material properties. Setup is the case where we will be applying boundary conditions. We will be selecting models for turbulence or multiphase or species, etc. Then the solution stage where we will be solving the governing equations by putting number of iterations, initializing everything. And the fourth step is post-processing, where after solving or after solution step we will be analyzing the results for the parameters for which we want to observe, such as velocities, pressure, temperature, etc. So the next question is, what are common boundary conditions which are used in CFD? So typical boundary conditions which are used are velocity inlet and pressure outlet. So in general, for every problem, velocity inlet and pressure outlet will be used. For alternative for the velocity inlet, there will be mass flow inlet. Okay. And vice versa also can be used, which is pressure inlet and mass flow outlet, or pressure inlet and velocity outlet. Okay, sometimes it is pressure in and pressure out also. So depending on our situations, these are the common boundary conditions which are used. Then another condition which is wall. So every wall will have no slip boundary condition first of all, and other than that it will have a heat flux or no heat flux. Okay, then there will be another boundary which is symmetry, which is zero normal gradient. Okay, next question is, what is wall boundary condition and what does no slip means? So a wall boundary condition represents a solid surface. So whenever there will be one solid surface, it will have a no slip conditions, which is that fluid velocity will be zero relative to that wall. That means that at exact location of the wall, the fluid velocity will be zero and it will grow gradually when it leaves the wall or as we move away from the wall. Okay, so to simply explain this, that fluid it sticks to the wall, which results in boundary layer development. So we have already seen what is boundary layer, how to resolve that boundary layer and everything. Okay, so this is related to the no slip condition of the wall. What is different between velocity inlet and mass flow inlet? So velocity inlet will directly give you the option that how much my flow velocity is and in which direction the fluid is going to flow. On the other hand, mass flow inlet specifies that what is the mass flow rate at which my flow is entering my system or my domain. So velocity will be in the meter per seconds unit and mass flow will be in kg per seconds unit. So your velocity will be dependent on the area from which your inlet is. So mass flow inlets are often for the better for the system when you want to control the amount of fluids inside which are entering into the system. So that the fluid's velocity will be directly calculated based on this mass flow and the area of the inlet. Next question is, what is symmetry boundary and when it is used? So symmetry is the boundary condition which is used, okay, which assumes that there is no flow or heat transfer across the plane and it mirrors the solution. So what it means is, so when you have the symmetric geometry and if you want to flow over that geometry, then instead of using the whole I can say whole object or whole body, you will be dividing it in a half. You will be performing simulation for that half part only. Okay, and you will give the symmetry boundary condition to the wall that you have been cut out your object over which you are performing the CFD. So the CFD software will replicate those results in that other half which is you have not used. Okay, so that's how symmetry boundary condition works. Then next question is, what is periodic boundary and where it is useful? So periodic boundaries are used when your flow pattern is repeating. That means if you have fan blades or if you have multiple tubes in a row, then you will be using periodic boundary. So it will reduce your computational effort. So where to use periodic boundaries? Suppose that you have 8 blades rotating in the some of the, you can say, tank or anything, and if you don't want to waste your computational resources, so what will you do is, if there are 8 blades, you will divide your domain into 8 parts equally based on the shape of your blade, okay, and then you will perform the CFD for only one part of that domain, which is 1/8 part of your total domain, and it will give you same result as of the total 8 blades, okay. That's how you will save your computational cost also. So this is periodic boundary. Next question is, what is a residual in CFD? So residual, you can plot the residuals in the CFD when your solution is running, and it will give you that how much your current solution is deviating from the exact conservation equation. So in the background, CFD solvers will be solving multiple equations which we learned earlier. So these equations will be solved, and it will measure that how much difference is there in between your current solution and the exact solution. This error which you see is the residual. So whenever your residuals are going very low, that means you are approaching your exact solutions, and which can be considered as that approach to the convergence. So now, what is convergence in CFD? So convergence means that whenever your solution is getting stabilized, okay, so you create one monitor point at the, suppose for at a outlet, where when you solve the CFD at the start of iterations, that parameter will vary much, okay, it will go up and down, and afterwards at some point it will be constant. So there are 3 to 4 ways where we can say that my solution is converged or my solution is perfect now, which, so for that you can use residuals, you can use monitor points, you can use mesh independent study, and etc and etc. Okay. Next question is, what is Courant number? So Courant number is a dimensionless number which is important for transient CFD analysis, okay. Transient is the time dependent CFD analysis. So this Courant number measures that how far a particle travels during one time step relative to the mesh size. So if the Courant number is too high, your solution may become unstable. So whenever you have a fluid particle moving in your domain, okay, the Courant number is calculating that how much that fluid particle is moving relative to your mesh size, okay. So depending on your mesh size, it calculates that. So if you keep your Courant number very high, then it will travel much faster compared to your mesh size, okay. So it won't be feasible, or it will be you can see you are moving towards an unstable solution. Hence your Courant number is always considered that it should be low, okay. Next is, what is post processing and what do you analyze? So in the post processing, we interpret our results. So whenever our solution is converged, we want to analyze that how my velocity or pressure or the temperature is varying in the domain. So how my flow is traveling from one point to another. I can study that using streamlines. I can plot many graphs which will be depending upon my requirement. I will be plotting many graphs. So whenever I want to study some parameters, or I want to interpret my results in some visual form, okay, I will be using post processing, and the parameters which I need to visualize, analyze, I will be using them. So the next question is, what is steady versus unsteady simulation? So steady simulations assume that we don't require time dependent solutions, which means that this phenomenon I want to study, I want it to be of the final state. So suppose, for example, I want to study the flow through the pipe. So I am studying this because I want to see how my velocity is changing, or how my pressure drop is happening inside the pipe, or how the temperature exchange is going on. So I want to see that effect in the steady state. I don't want it to be like if I start the tap now and how my flow will go at the start. I don't want that, okay. And another example, that if I am doing forced convection of any one, suppose battery pack or anything, then if I want to see that in first 30 seconds how my temperature is dropping, okay, from let's say from 50 degrees Celsius to 40 degrees Celsius, I want to see how my temperature is dropping in first 30 seconds, then in first 1 minute and everything, then it will be unsteady simulation, which is time dependent simulation. Okay, so which type of simulation we want to study will be totally dependent on steady or unsteady simulation. It will be totally dependent on your physical phenomenon which you want to capture. So the next question is, how do you validate the CFD results? So validation of the CFD results, it means that we have to prove that my CFD results are correct. Okay, so that can be done by comparing my results with experimental data or theoretical calculations. So I have to see that if my simulation reflects the real life behavior. Without validation, your CFD results are just guesses, or you can say as per your CFD line, you have used every condition perfectly. Okay, and based on convergence, mesh independence, everything, you can say my CFD results are correct. But to validate them, you will need some kind of experimental data or theoretical calculations. So thank you for listening to the part 3. Please like, share and subscribe, and don't forget to hit the bell icon. You can suggest the topics you want to study or any simulation you want from my side. You can tell me in the comments. Okay, thank you.